Hello, everybody. I'm Ted Letofsky. I'm with Evolving Solutions. I'm an architect here at Evolving, and I'm back again with Steve Solwin. He's an architect and worldwide resource for IBM, and we're here today to talk about the IBM Flash Systems Flash System 9200. If you missed the first blog, we're going to do just a few seconds of history. Essentially, the Flash Systems FS 9200 is the unique fusion of three different product families come together in a new form factor. It's the software and firmware that came out of the IBM SAN Volume Controller SVC IBM virtualized platform. It is the GUI and command line tool set that came out of the IBM Accelerate and XIV platform, and the back-end flash technology that came out of IBM's Texas Memory Systems acquisition that is now called Flash Core Memory Modules. All of that comes up in a 2U form factor. And one of the things that we really want to start talking about is that the IBM Flash Systems family, particularly the FS9200, supports NVMe. And that involves two different but equally important conversations. The first is that the midplane and back end of the Flash Systems 9200 is NVMe compliant. That means that the storage itself that's inside the flash core drives themselves speak to the controller through NVMe. It also is important to note that the Flash Systems 9200 is NVMe over Fabric compliant, whether that's in Fiber Channel or in iSCSI. So first, let's go back and talk about NVMe. And Steve, go ahead.
So NVMe is a new protocol, and it was needed for a number of reasons. But you think about, even when we're talking about Fiber Channel devices, we're actually still talking SCSI command set. And the SCSI command set is great. It does a lot of good things, but the SCSI command set was old back before the beard was gray. So NVMe is new. It is designed specifically to talk to flash devices. So there's a whole slew of stuff, right? Because SCSI talks to tape, and I don't need to rewind and reposition. I don't need to seek, right? So a whole bunch of that we don't have to do anymore. And that benefit of that, making that very simple command set, gives us two different but related benefits. The other part of that that helps provide the benefit is we now have a very, very wide cache layer or definition. I have 64,000 queues, not cache, queues, and they're each pretty deep. Now, the deep part I don't get. I'll be up front. We need queues because the storage was slower than the processor. We needed to queue up commands, and it needed to go on and do other things. So I don't really believe I need a deep queue depth with something that's talking to flash. But they must have liked 64,000 because they did 64,000 queues at 64,000 deep. So those are the kind of the two things that bring this benefit. The first benefit is really simple to see, and we've done a technology demonstration to show this. I take a server talking over Fiber Channel to IBM Flash System storage, and they're using SCSI. They're using Fiber Channel, and I run a workload, and I get 100,000 IOPS, and I get a specific response time that's related to that workload. All I do is switch to a different driver. So all the hardware stays the same, the Fiber Channel adapter, the switch, the storage, everything stays the same. I just change, now I'm using an NVMe over Fiber driver. Same 100,000 IOPS, maybe a little bit more. But the important things for that same 100,000 IOPS at about the same response time, I look over at my server and I see somewhere between a 20 to 50% drop in CPU cycles. So because the CPU is doing much less manipulation of the protocol to talk to the storage, it is way less busy. So if I implement NVMe over fiber channel, I can essentially, depending on workload, I can get 20 to 50% more work out of my existing infrastructure because it's spending less time dealing with a very deep protocol as opposed to now using a very minimized protocol. So that's benefit one.
So let me interject there for a moment. Let me make sure that I understand exactly what you said. That if all other things are equal, the same storage, the same interconnect switches, the same host adapters, if I use NVMe over Fabric as opposed to using fiber channel or traditional iSCSI, if I'm doing apples to apples and the only thing that changes is that I'm doing NVMe over Fabric, I will likely see a small improvement in IOPS. I will likely see an improvement in latency because the command set itself is thinner and lighter than the old one. But the real value, the real benefit is that the host operating system is doing less work to communicate with the backend storage. And as a result, I actually can get more useful work out of the same compute platform because of that.
Exactly correct. Exactly correct.
Outstanding.
And that benefit we can show right now with existing operating systems. And this is one of those things where NVMe has been around for a while now, not a long time, but a while. It takes a while to get the standard built in. But so Fabric knew about it, adapters knew about it, storage knew about it and implemented it. And we saw a very prominent lag in the operating systems picking up and taking advantage of it. Well, that has since changed. So we can demonstrate what I just talked about today using existing hardware, existing operating systems. What I'm going to talk about next isn't there yet, but we're talking about what we can do. Think about a virtualized environment, or I'll call it a containerized environment to keep the syntax correct or consistent. I have a bunch of different things doing a bunch of different work, and I get the what I call the I/O blender effect, where all that I/O from all those different things comes into a single pipe and then goes to the storage, and that's okay. It works, but I lose a lot of ability to really understand what's going on in each of those separate entities without going in and doing a lot more looking and working at finding that information out. I can take now, with 64,000 queues, I can assign a queue to every virtual machine, or I can assign a queue to every container. Again, this is something that we're talking about, not something that's implemented yet. But think about two things. One, I now have the ability to have a better visibility into what's going on in each of those separate work environments. But I think more importantly, from an overall performance perspective, I have the ability to not have to do context switching to move information to get to information in one queue or another. I have a queue that's assigned to that container, and whether it's doing work or not, I don't have to switch anything. I just go to that queue and pull up what's on the top of that queue and use it and fulfill the requirement there. So those are the two benefits. One is immediate, it's there right now. The other is in the future as those environments take advantage of that huge amount of queues that we have available with NVMe.
All right, so actually let's take a big hop back for a second. So we talked about NVMe and we've talked about NVMe over Fabric. Let's go back to talking about NVMe. We talked earlier that storage, like a hard drive, often speaks, so when we're talking about parallel SCSI or SAS SCSI or fiber channel, we're talking about a device talking to a host adapter. And in NVMe, that's the original limit of the protocol. NVMe was meant for flash devices and only solid state devices to talk to the computer. So NVMe drives inside a server. And because the protocol of SCSI was so old, so long in the beard, that it had commands for tape, it had commands for seek, it had commands for robots, it had commands for, God help us, it had commands for scanners and old printers, that there was a lot of overhead in the command, and necessarily built into the command was also some latency to wait for commands to respond. So NVMe is meant to be a protocol that really only works with flash. It can't be used direct from host adapter to storage if the device is a spinning disk. But NVMe by itself isn't capable of getting out across a fabric, out across a storage network, whether it's an IP network or whether it's a fiber channel network. NVMe over Fabric, on the other hand, is designed to do just that. It's designed to encapsulate and expand NVMe communication across a fabric, whether that fabric is a fiber channel fabric or whether it's an Ethernet fabric, and there's two different primary competing standards, RoCE and iWarp today. But in both of those universes, I'm still doing exactly the same thing. I'm using a very stripped down, very latent, free protocol to communicate from compute back to storage. And once upon a time, storage, even the best spinning disk storage, was pretty slow. We queued commands, we buffered them all up because it was easy for compute to start to overrun storage. Well, now in a post-flash universe, our storage is very often as fast or faster than our compute asks for, right?
Right. Again, and that's my comment about not needing a queue that's 64,000 deep.
Right.
We're taking advantage of a bunch of them that's spread quite wide.
So instead, what you're telling me then is that given this post-flash universe, the depth of queuing might or might not be as interesting to a user, but the massive parallelization, the breadth of all of these different concurrent simultaneous IOs back to an NVMe over Fabric compliant storage environment is really interesting, because now we are working towards the capability of being able to granularly assign queues directly to a virtual machine or a container or a given workload.
Correct. Yeah. Very, very cool.
And we think that that's pretty exciting. We think that that's a real game changer. So thank you guys for listening. Again, I'm Ted Letofsky, Steve Solwin.
I'm Steve Solwin.
You guys have a good day. We'll talk to you soon. Thank you.
Bye now.